In this episode, we're going to talk about sound intensity, which is the amount of sound pressure energy that a sound has as it's traveling through space. The goals we have for this episode are to differentiate the terms intensity and loudness, which are words that you might have thought mean the same thing, but actually refer to different concepts. We're going to understand what it means to hear things logarithmically and why we use a logarithmic scale, the decibel scale. We'll think about what a decibel is and learn some common landmarks for different decibel levels of different sounds that are familiar. First, let's think about those terms. Loudness is our subjective impression of the energy of a sound, and of course depends on the intensity of the sound as well as your hearing level. So if you have some hearing loss, you might not perceive something to be as loud. But objectively speaking, intensity is what we can measure. So no matter who is listening, as long as their instruments have the same reliability, they'll get the same measurement for the intensity. This would be the actual movement and change in sound pressure that we perceive in the air. On the screen here, we have a range of different sound pressures on the Pascal scale. So these are representing the lowest to highest amount of sound pressure that we would normally encounter. And so we can see on the left this very small number, 0.00002. So you might think that we scale differences in sound intensity by increments of that small number, which would bring us to 0.000004, 8, 10, 12, 14, 16, 18, and finally to the next number in our sequence. So, we have 10 increments here between those numbers, including both endpoints. But if you jump forward in the scale, we have 100 increments for the next step up in our scale, and then 1,000 increments, 10,000, 100,000, and finally 1 million increments. And so the upper end of this scale is literally 1 million times the value at the lower end. So you can imagine that this could be pretty cumbersome to keep track of things which extend down at the lower level to have 4 zeros after the decimal, and then a small number like 20 up at the upper end. So just to use our intuition here, the way that we normally scale things is with pretty small numbers. 5 stars, a scale from 1 to 10, a rating scale with 5 different units, or we use percentages, right? So things out of 100. That's about as high as we normally go. So we like scales out of 100, and if we use the scale out of 1 million, we'd say like 850,000 people out of 1 million have hard water, and 300,000 of those people use a water softener. It's obviously easier just to say 85% and 30%. So it's nice to have a 1 to 100 scale. We use this in colloquial language, we use this for grading exams. And when we think about what it means to use a scale, what we're talking about is keeping track of changes. And I would add further that what we're trying to do is keep track of meaningful changes. So let's leverage our intuition a little bit more. Suppose you have 43 cents. Maybe you're just thinking about what you want to get out of a vending machine. How much money would you need before you say, now you have more money? Maybe you need just 57 more cents to get something that costs $1. Not much, really, in the grand scheme of things. If you had $43, you might have a different answer to that same question. How much money do you need before you'd say, now you have more money? A comparison of $43 versus $43.57 doesn't really seem like anything that's very different. Now you have $43,000. Maybe you're negotiating the starting salary for a new job. How much more money would you say you would negotiate for to get more money? Certainly you wouldn't negotiate from $43,000 to $43,057. So when we think about differences, we're always scaling them with a reference point from where we're starting. This kind of scaling also shows up in classifications. Here again we have a money example, but what we're looking at is different strata of income levels and their relative audit rates. I care less about the audit rates, but let's think about those different categories of income level. The first few scale in increments of 25,000. But if we went from 25,000 all the way up to the largest number of 10 million or more, we would have so many categories on here that it would really be cumbersome to use this chart. Instead, as you can see here, once we get past 100,000, we're no longer using increments of 25,000. Now we're using an increment of 100,000, 300,000, 500,000, and then finally 4 million, 5 million. So the increments actually get larger. They don't get larger in a proportionally equal way, but we can see the concept here. The opposite of this would be linear thinking. So in a linear system, you'd say 1 is to 2 as 100 is to 101. Both of them are just 1 apart from each other. 50 is to 100 as 500 is to 550. Again, these are just 50 units apart from each other. And 40 is to 120 as 5 is to 85, because these are just 80 apart. So this style of linear thinking just means that the same difference means the same thing, regardless of your starting point. But the opposite of this would be logarithmic thinking. So as opposed to 1 is to 2 as 100 is to 101, we'd say 1 is to 2 as 100 is to 200, because just as you've doubled 1 to get 2, you double 100 to get 200. 50 is to 100 as 500 is to 1,000. We're doubling again. Here, we're just tripling, right? 40 is to 120 as 5 is to 15. This is an example of logarithmic or proportional scaling. And so when we go back to our differences in sound pressure, what we're trying to think of is proportional scaling. Each of the increments we see on the screen here, from 4 decimals then 2, 3 decimals then 2, 2 decimals then 2, each one is just a scaling of multiplying by 10. So as it turns out, we hear differences in sound pressure logarithmically. This means that the same range of loudness difference corresponds to a proportional change of equivalent size. So what we're saying here is changing from 0.00002 to 0.0002 is the same as changing from 2 to 20. Some other little details as we're thinking about this is that we are differentially sensitive to sounds depending on their frequency. So here's where we get one example of how intensity is different than loudness. A sound that's between 1,000 and 4,000 hertz will sound louder to us than a sound that is lower or higher than those frequencies, even if the sound pressure level is the same. So this is just returning back to our terms, where intensity refers to the physical magnitude of sound energy, and loudness refers to your perceptual or subjective magnitude of sound energy. In this unit, we're really not going to talk so much about loudness. However, loudness does play a little bit of a role here in how we measure intensity. Specifically in this starting example of thinking about 0 decibels. 0 dB sound pressure doesn't mean no sound. It means the lowest intensity of sound that is just audible by people with typical hearing. This is what we'd call a threshold. And as it turns out, changes in decibels can go down below 0. So negative 20 decibels refers to a sound whose pressure level is 1/10 what we would need for 0 decibels. And some people can actually hear those sounds. Conversely, 20 decibels in the positive direction refers to a sound whose pressure level is 10 times what we need for 0 decibels. So again, notice that we're thinking in proportions because we're multiplying by 10 or dividing by 10 as opposed to adding and subtracting. So let's think about what it means to call something a decibel. The technical definition is 20 times the logarithm base 10 of a ratio between the sound pressure and the reference pressure. So if this makes you kind of woozy, let's start to break this down. The 20 is easy. We're multiplying 20 by something, and the something is the log of a proportion. We'll get to the log in a minute, but let's just understand what this proportion is. It's sound pressure over a reference, and that reference pressure is that super tiny number that we keep referring to. So this number will help us form a proportion. Let's suppose, we think of this as just the denominator. But if we have a pressure that's twice that, right? If we have 0.00004 pascals, we just put that as the numerator, and this is obviously just a ratio of 2. So if we take the log of 2 and multiply it by 20, we'd get our answer. But the log base 10 of 2 is, I don't even know what that is. I can't think of that off the top of my head. So let's think of something that's a little easier. Suppose we have this number for our air pressure. We have 0.0002 pascals. So we can see that if we put that as the numerator, our ratio now is 10. So this becomes a lot easier because when we think about log base 10, what we're saying is 10 to the power of what gives you that number? Well, in this case, 10 to the power of 1 gives us 10 because it's just 10. So 20 times 1 will give us a result of 20 decibels. So if we have that amount of pressure, 0.0002, that means we have a 20 decibel sound. Let's take another ratio here. Suppose we multiply that by 10 again. This time our ratio is going to be 100. And now what we can do still in the same style, we say 10 raised to what power gets you to 100? And this is raised to the power of 2. 10 squared is 100. So 20 times 2 gives us 40 decibels. Now let's take a much larger number. Let's put the 2 right after the decimal place. As it turns out here, our ratio is 10,000. You multiply our reference level, the tiny number at the bottom, by 10,000, and now you'll get this 0.2. So 10 raised to what power gives us 10,000? It's 4. So we multiply 20 by 4, and we get 80 decibels that correspond to this number here. So we can keep producing these ratios, but the example I really want to get to here is the case where you have exactly that reference amount of air pressure. Well, what this means is that you have a ratio of 1. So 10 raised to what power equals 1? As it turns out, any number raised to the power of 0 equals 1. So 20 times 0 gives us 0 decibels. So 0 decibels doesn't mean no air pressure, doesn't mean no sound. It means that the level of air pressure you have is exactly equal to the reference pressure that we compare everything else to. So this would be the lowest amount of sound that you can expect to hear if you have typical healthy hearing. Just to recap here, a ratio of 1,000 gives us a scaling of 10 to the third. So 3 times 20 is 60 decibels. A ratio of 100, that would be 10 to the second. So 2 times 20 is 40. A ratio of just 10 is just 10 to the first. That would be 20 decibels. And a ratio of 1, meaning you have the same number, that's 10 to the 0, meaning 0 decibels. The dynamic range of loudness refers to the range of intensities spanning from just what you can barely hear up until the highest you can take before it starts being painful. And in typical listeners, this spans from about 0 decibels HL to about 100 or sometimes even 120 decibels HL, which you could consider to be, very uncomfortable. The HL here refers to a scale that is referenced to different levels of hearing that you can expect in a typical population, which is to say that they've been automatically corrected for the fact that sounds of different frequency refer to different sound pressure levels. We won't really dive into that in this episode, but it's just to make sure we know that when we're expressing decibels, we really should be using a unit. So what I want you to get out of this episode here is remembering that sound intensity scales proportionally so that the unit of intensity is a ratio, not a linear difference or not an amount of pressure. 0 decibels doesn't mean no sound or no air pressure. It means the lowest amount of sound pressure that is audible by typical listeners. You want to remember that a 10 times multiplication in sound pressure results in a change of 20 decibels. And we have some simple examples to remember for powers of 10. So the amount of powers of 10 times 20 equals your change in decibels. So you want to remember things like the log base 10 of 1,000 is 3, the log base 10 of 704, I'm not going to ask you to remember that because that's not something you can really just figure out in your head. So for easy log base 10 numbers, I'll expect you to know what that is, because in this case it's just 1 followed by 3 zeros. Those are the ones I'll expect. I won't expect you to calculate logarithms in your head, because we can just know what, we can use a calculator for that. I really want you to know the strategy of converting these numbers. And finally, remembering that what we mean by dynamic range is the extent of sound intensities ranging from the lowest audible to the highest that is just barely comfortable, which typically goes from 0 to 100 or 0 to 120. In the next few slides here, we just have some common reference points for different sound intensities. What we have in this center column is the actual pressure. So again, ranging from the threshold of hearing at 0.00002 all the way up to a sound that you'd never really want to hear from this close, which would be a jet aircraft. So revealing the corresponding changes in decibels, what we have is basically what we really are aiming for, which is a 0 to 100 scale. So the other things above 100 are really things that you wouldn't really encounter on a day-to-day basis unless you're, in your profession, you use a chainsaw. But for the rest of us, we're basically hearing soft sounds like leaves or background noise. The sound of even just the sound of a quiet library is already about 40 decibels. Conversation is, just 20 decibels higher than that, meaning it's 10 times the amount of sound energy. And we have some other examples on the screen here. So there are a lot of different reference scales that you can find online. These are just some that I find to be pretty useful. And this one, what I like is just reminding us that as you get up to the higher end of the scale, we are talking about millions, tens of millions, hundreds of millions of times the amount of air pressure that we can hear. So when we're thinking about the loudest sound recorded, the eruption of Krakatoa, we're thinking about 180 decibels. So, a nuclear bomb ranges somewhere between, in the upper 100s to about 250 decibels. So if you find yourself calculating an amount of decibels that's, in the hundreds or thousands, you might want to take a step back and remember that our scale really only goes for normal sounds up to about 100 or a little bit above.